This is topic 5.2, capacitance, part 1, which will focus on the idea of what a capacitor is and the concept of capacitance. The next short video will focus on the factors that affect capacitance and how they can alter energy or capacitance. So to give an idea of what a capacitor is, let's take a look at the picture. Alright, so you see small capacitors that are found in microelectronics, small circuits, and then you have large ones, which can be found in air conditioning units, disposable cameras, anything that needs a real quick discharge of energy. So what a capacitor essentially does is store charge to be used sometime later. It can be a few minutes, it can be a few hours, it can be days, and give you, depending on use, a large discharge, quick discharge of energy. Very different in a battery, which doesn't have charge stored in it, but rather use chemical potential energy to move charges around and transfer energy. So let's take a look at a quick clip of what a capacitor can do in a fairly extreme way. So here he shows a capacitor. It's already been charged, all right, and it's touched across the positive and negative. Something happened very quickly, so let's slow it down. And you get a very, very quick release of energy. If you're not careful and you touch those two leads with your fingers, you can get quite a shock and knock you out. It can be quite dangerous. So this diagram shows what the heart of a capacitor is. The reason these take on the shapes is they take a sandwich of conductor, insulator, conductor, and they roll them up into a very condensed volume, so hence the alternative name condenser, and it gives us a lot of area in which we can store charge. So the insulator part between them can be any good insulator. The fancy term is dielectric, but for what we're going to study, we're going to look at either air or a vacuum. So let's take a look at this at a close-up and a much simpler view. Okay, so we're going to look at it in terms of parallel plates, something we've looked at before. So the diagram on the left shows two parallel plates that are going to be eventually hooked up to a voltage source. Let's draw in a voltage source right here. Let's say we have a positive terminal, we have a negative terminal, and we connect it up. So what the voltage source will do is, in essence, it will draw positives from the positive terminal. Okay, work is being done by the voltage source. And in the process, depending on how you look at it, but look at it through induction, it's going to draw negatives because of the electric field across the plates from the negative terminal. And of course we have an electric field. And the electric field is uniform because we have parallel plates. Now when we talked about electric fields last year, it was the idea of using the uniform field to take a negatively charged particle, let's say, or positive, and accelerate it across, okay, with some force and give it kinetic energy. Capacitors, on the other hand, aren't so much interested in the field between them, but that's important. It's using the charges externally to release energy when we disconnect the voltage source. Okay, so let's take a look at this a little bit more, relationship between the charge that you put on a capacitor and the amount of voltage you put across it. Okay. So let's reconnect our voltage source and look at this a little bit more systematically. So let's say we have a variable voltage source and our initial voltage is 1 volt. Okay, and because of the 1 volt we deposit a certain amount of charge on there, let's just say 2 units. And of course, because of induction, we must have an equal amount of negative there. If we decide to crank up the voltage to, let's say, 2 volts, not surprisingly, we will see that we'll have twice the charge. And if we go up to 3 volts, then we just keep adding a proportional amount of charge, so that if we go to graph charge versus voltage, we would expect a linear relationship. And from any linear relationship, we can make an equation that relates these two important variables. And of course, the key thing to make the relationship is the slope, which is nothing more than a ratio of the change in charge over voltage. And this, by definition, is called capacitance. Good handwriting. Okay, and then we can make a very simple equation that defines capacitance, capital C, and that's nothing more than a ratio of charge to voltage on these plates. Alright, this says nothing about how much charge we can put on it or how much voltage, but we know that for a given setup, more voltage, you get a proportional amount of charge. Now units, as one can see in the equation, would be coulombs per volt. Don't let the C's throw you off. This is the symbol for capacitance in equation. This is the symbol for charge in units. Alright, and that is called a farad, after Michael Faraday, and it is given the symbol capital F. Alright, so we've got charge stored on parallel plates that can be used externally if we touch the positive and negative terminal. So why would we want to do that? Well, one of the primary uses is you can store energy. So as you increase voltage, not only does charge increase, so does the amount of energy. Okay, and in capacitors we give energy the symbol capital U. Alright, and again we want to use it externally. So we want to develop an equation for this. Well, if we go back to what we learned last year with parallel plates, okay, anytime you have a voltage, okay, across the plates or external to the plates, and you have charge there, then there's a simple relationship between that charge and voltage. It was the product of the two. But because of this linear relationship between charge and voltage, if we want to find the amount of energy stored, we would do the area under the graph, and we see that that's a triangle, and since it's a triangle, there's going to be a 1/2 QV aspect to that. So that's a little bit different than what we learned last year. So let's write that down, equation 2a. Alright, the energy stored in a capacitor is 1/2 Q times V. And we can express this another way because very often we don't know how much charge is stored in a capacitor, but rather we know the capacitance of the capacitor. So it would be useful to express it in terms of capacitance. So we know from the previous equation that the amount of charge stored is equivalent to the capacitance times voltage. So then if we substitute that into for Q, we see that U equals 1/2 C times V. That's our Q value times V, and of course that's 1/2 CV squared. And that tells us something important about how much energy is stored as a function of voltage. It goes by the square of it. So doubling voltage doesn't give you twice the energy as one might expect. You get 4 times. And if you go up to this equation, you might say, well, wait a second, that doesn't seem to say that. This seems to suggest twice the voltage gives you twice the energy. Remember, if you double the voltage, you're also doubling the charge, so 2 times 2 gives us 4. So they're saying the same thing, but it's not as obvious with the first equation. Alright, so let's do a practice problem. Okay, very basic at first. Let's say if I've demonstrated to you already, or I will demonstrate, we have a bank of capacitors which has an effective capacitance, not of 460 millifarads, but rather 460 microfarads, and it is charged with 330 volts of potential. So the simple question we ask is how much charge will they hold? Okay, so if we go back to our first equation that relates capacitance, voltage, and charge, we have Q equals CV, which will be 460, make sure we take care of the micro, times 10 to the negative 6 farads, times 330 volts, and we get a surprisingly large value for the charge, 0.15 coulombs. Okay? Remember, full coulomb is like a lightning bolt, so this is a little bit more than 1/10 of that, so that's quite a bit of charge. Most capacitors, especially used in small circuits, are on the much smaller range, anywhere from, let's say, typically microfarads all the way down to picofarad. Alright, so the next question we can ask is how much energy is stored in here, and again, fairly straightforward. Energy is U. We can use 1/2 QV, we can ask 1/2 CV squared. We have all the information, so let's take 1/2 Q times V. Okay, so 1/2 0.15 coulombs times 330 volts. Let's try to make this a little bit more legible. And you punch in the numbers, and we get a fairly large number for such a small device. 25 joules is quite a bit of energy for the device that you saw in the YouTube clip. Like many quantities that are defined as a ratio of two other quantities, in other words, capacitance is defined as the ratio of Q over V. The actual value of C does not depend on Q or V. This is very similar to resistance, which is defined as the ratio of voltage to current. We learned last year that resistance depends on the properties of the resistor itself. We will see that capacitance, while it doesn't depend on charge or voltage, okay, it does depend on the properties of the capacitor itself. Okay, and this will lead to an alternate definition of C, which we're going to investigate in the next lesson.